So good morning, everybody, and welcome to the first session of the second day of the symposium. It is my great pleasure to introduce the first speaker of this session, Professor Hendrik Lensch from Tübingen University. Professor Lensch is an expert in inverse rendering as well as image-based rendering. Please.
Thank you very much for the introduction and for the invitation. So after we've seen that, probably should just keep it closer. Okay. So after we've seen lots of interesting talks yesterday on material perception, I'm just going to give you my point of view on the interaction of material and illumination from the measurement perspective. So what my task really is, or some big part of my research is on creating photorealistic models of real-world scenes, which can afterwards be re-illuminated correctly to render photorealistic images. And by that, we basically capture all visual properties there are about a particular material, about a particular scene. Okay, so here's the famous sky disk of Nebra, the oldest depiction of stellar constellations by mankind, actually. So, and this is the backside, which nobody sees typically in the museum. Okay, so we are trying to measure this kind of reflectance. And my talk then mostly will focus on multispectral reflectance and fluorescence. But let's first look into what we are actually dealing with here. So in computer graphics, there is a famous rendering equation you see up there, which can describe easily that the light leaving a point X into a direction omega O corresponds to the light that is emitted, LE, into that direction, plus all the light that's reflected at the point, collecting all the light from all incoming directions, reflecting it towards the outgoing direction. Okay, so you have the integral over all directions over the incident light times the BRDF, the reflectance property. And you can formulate that easily in terms of linear operators, so that the light field in the scene that you're going to observe corresponds to the light that is emitted in the scene plus the light, again, being reflected in the scene. Okay, so and you have here just this linear system of equation, and the typical way how you can solve it is, for example, you start off taking the light that's emitted by light sources, reflect that light once by all surfaces of the scene, then twice, and so forth and so forth. So really spelling it up as interreflections accumulating. And the stuff we are measuring, actually, is the so-called light field, or reflectance field, which sort of is then the inverse of this operator, of the identity minus the reflectance operator. And that's what we are actually measuring theoretically. So now let's make it very easy terms again. So reflectance field have been introduced by Paul Debevec, actually. So it's as easy as follows. You just capture an object illuminated from distant illumination from different directions. For each direction, you capture one image. And then Paul Debevec showed that you can easily sort of render a novel image of the scene, correctly illuminated in this environment of all lights on at the same time, but just superimposing all the images. And if you now sort of even multiply each image by a specific color, then of course you can reproduce colorful illumination from the environment and simulate how the object is going to look like. And we've done our share of work in that field as well. So here you see a real scene from which we captured a high-resolution reflectance field so that you can render the scene photorealistically in two completely different virtual environments. The one is actually St. Paul's Cathedral, and the other one is the church in Stanford. So, of course, the scene has never been in either of these two places, but we can correctly simulate all reflections, all refractions, all interreflections, as well as translucency effects. So, having this kind of measurements of the reflectance field, we are able to produce all possible visual stimuli of that particular scene in arbitrary illumination conditions. If you go a step further, you can actually say, okay, we are not just interested in how the scene behaves with respect to distant illumination from point light sources, but really if we eliminate individual light rays and really scan the surface, okay, so we can sort of use a bunch of projectors, illuminating the scene now pixel by pixel from the projector and recording images, and then superimposing these images in order to simulate how the scene would look like if we project a spatial illumination pattern, like you see it here from that projector over there. And by that, we can actually simulate how light's going to be, light rays, individual light rays, going to be refracted and reflected of scenes. Okay, so we can have spatial, high spatial frequency illumination inside the scene and simulate that part. Okay, and simulate it correctly. Why I show this part of research again is I want to drill down on this particular structure of a reflectance field you're typically going to observe. Okay, so here's the sort of simplest case of a reflectance field you can imagine, that is just a printed sheet of paper. So what could happen if you illuminate a point along this white line? Well, you're going to see a reflection where you illuminate the point, and the rest of the paper will just be black if there's no other light source. Okay? So the reflectance field simply is going to be this diagonal, where along the diagonal, you just have recorded the reflectance of the scene. And in any part which is not along the diagonal, that means you're illuminating one point and measure the reflected light and another point, it's just going to be black, because on a sheet of paper there's absolutely no interreflection happening. This completely changes if you have a concave object, this open book. Okay, so then of course you again see this major dominant diagonal where you see the direct reflection happening, and then you have the off-diagonal part, that is, you illuminate a point here on the side of the book, and then it re-illuminates the other half of the book diffusely. And since it's a diffuse process, it's actually smooth, okay? So therefore, any part in here is not perfectly dark, but it's boring because there's no high frequency information anymore. Okay, and we're gonna explore that part further in our measurement setup in order to reduce the measurement effort. Okay, so there's lots of interesting structure inside a reflectance field, direct versus indirect illumination, spatial versus angular resolution, and what I'm going to present next is sort of like multispectral and bispectral reflectance. So after having done all this work on directional and spatial angular resolution and reflectance, we actually figured out that we didn't cover quite a large class of materials so far, namely all those materials which reflect light not at the same wavelengths of the incident illumination, but actually turn the incident wavelengths into some other re-emitted wavelengths. And the main effect, of course, is for fluorescence to sort of have signaling colors. Okay, so the three balls you see here sort of are all three fluorescents. And if you compare that to the intensity of a 90% white patch, you see that they are much, much brighter than any surface ought to be. If it just would reflect 100% light, this thing is even brighter. Okay, and how is that? Well, it takes energy from one part of the spectrum, potentially the non-visible spectrum, and re-emits it inside the visible spectrum. And therefore, it can produce larger amounts of energy at particular wavelengths than a 100% reflector. So, and fluorescent materials actually are all over the place. If you look around here, you actually see lots of white shirts, which are nicely fluorescent. You see paper. You have your teeth, which are highly fluorescent, and so forth. And it was interesting that in computer graphics, this effect has mostly been neglected for decades, even though it really appears in almost any room. Any man-made object easily fluoresces. Particular plastics, most plastics actually. So here's the physical background, what's happening. We have a photon coming in with some high energy, and the energy sort of excites an electron to some state, and then fluorescent materials have this so-called Stokes shift, so the energy of this electron drops down to an intermediate state, and from there on it drops down again and re-emits a photon, but now of less energy. Okay, so it's always a wavelength transport from shorter wavelengths, that is higher energy, to longer wavelengths, lower energy. And if you look at this, you have a particular absorption spectrum for each particular material. And then from that, it's converted into an emission spectrum based on this fluorescence. Okay? So they can partially overlap, but this means that really there's absolutely no photon. There's probably a photon in this range, which then gets re-emitted at this range. So they cannot be inverted clearly. So this effect, of course, has been also studied in physics. And there is the so-called Donaldson matrix or re-emission matrix, which tells you how much light is being reflected for the incident versus the outgoing wavelengths. And of course, this is a lower triangular matrix. That is, along the diagonal, you have light being reflected at exactly the same wavelength that comes in. And in the lower, so that mostly corresponds to standard reflection, if you want to. And you have the re-emission part, which is then due to fluorescence, which is in the lower bottom triangle. And you see here now that there's some transport from the blue light towards red. Okay, that's how you read it, actually. And this is how the red part overall can reflect or re-emit more light than you would actually just have by pure reflection. So even in this fluorescent part, actually, we can see some angular distribution. So there are some phase functions associated with fluorescent molecules that can be oriented, and depending on what kind of material you have in front of you, you might actually be able to observe this effect. Or way more common is you have a particular layered surface with some lacquer on top, which then turns this fluorescence, which could be isotropic and therefore diffuse and boring angular-wise, into something which is, again, more interesting. That's exactly what we try to explore. Like, how much angular dependence is there for fluorescence, and how can we make use of that? So we would like to measure both the spectral response and all that angularly resolved. And we try to make an efficient acquisition scheme out of that. As I earlier said, though, in computer graphics, the work on fluorescence really could be described by these few papers. There was really hardly anything else around. And still, if you look, like only a couple of years ago, the first spectral renderers overall appeared, okay? Let alone bispectral renderers, which you really need here, where we can simulate an incoming spectrum and produce a returning outgoing spectrum. So how can we model that? Well, let's start again with the rendering equation. So here again, we are interested in the light that's reflected. Now I left out the position on the surface, okay? So just into some direction, it's the emitted light plus all the light that is reflected. That's just for standard surface reflection, okay? And the interesting part about this equation is that here the incident or the reflected light sort of can be the incident light on some other part of the scene, okay? So some light that is reflected off this point easily will re-illuminate a point on the other half of the scene, and therefore you have this integral equation of the Fredholm integral equation of the second kind, actually. So this is called the BRDF, which just describes reflectance. Now, of course, it's easy to extend that to the spectral render equation, where you just add a single wavelength parameter to all of your terms, and then can, not only for red, green, blue, but for all possible wavelengths, simulate how this light transport happens. Okay, so that's easy enough. What we will actually have to do is, well, we have to figure out that we're probably going to need spectral illumination in order to really measure that, or measure spectral reflectance by having a multispectral camera. What I'm going to argue is that you should always use spectral illumination, because then you can cover way more effects than if you just had a spectral camera for measuring reflectance. Because what we really would like to measure is this bispectral reflectance. That is, we want to know what is the outgoing spectral radiance, which of course again is the emitted part, plus now the reflected and re-emitted part of a way more complex object, this BRRDF as we named it, which now depends on both the incident and the outgoing wavelengths. And now of course you have this double integral both over the space of all incoming directions as well as of all incoming wavelengths. By that you also changed sort of just the unit of this term. So how do we measure that? Well, in the tradition of measuring BRDFs in an image-based scheme, we took a curved sample of a homogeneous material first. Okay, so here we have a fluorescent sphere of one particular material, and then we had a multispectral light source, which was a white light source, an HMI bulb with a spectral filter, and then we put a set of UV LEDs as well in order to sort of illuminate in a non-visible range, which is particularly useful for fluorescence because transport from the non-visible to the visible. And then we had this spectral camera for recording all that. So the type of data sets we get from that is sort of like a Donaldson matrix, but now with the BRDF for each pair of incident and outgoing wavelengths. Okay, so at each possible position here in the matrix, you have the full BRDF describing how much light it actually is going to be reflected in which particular range. And you clearly see that the specular highlights are here on the main diagonal because they typically, for non-metals or dielectrics, actually sort of keep the wavelength. And the fluorescent part then is here on the bottom. The problem of that approach is, of course, it takes ages to acquire such kind of data. So you have to imagine you have a white light source. Out of that light source, you crop out a narrow band, almost monochromatic part of the spectrum, okay? And then you observe that through, again, a very narrow band spectral filter, okay? So by that, we are sort of talking about 3 seconds or 8 seconds exposure time with cooled cameras. And if you then have 170 pairs, you're easily going to be at 2 days of acquisition for a single material. So what we did is we looked at how the structure of this fluorescence actually behave. And there have been, in the literature, you can find hints that people try to just say, okay, you can separate it into a part which just expresses fluorescence and another part which just expresses the angular dependency. However, we found out that's not the case for almost all materials we had at hand. It's not just the decomposition into these two, but you can, of course, easily sort of do a PCA and then just add a couple of more of these kinds of terms and then sort of like get a fast acquisition. So what you do is now, like most often we're going to see a reflectance BRDF plus some fluorescence part, which sort of more or less keep the bispectral re-emission, actually. And this is for a couple of materials, these are the basis sets we're going to get out there. So in order to speed up acquisition, we have to not only measure all pairs of incident and outgoing wavelengths, but we also have to rotate our camera to lots of different locations in order to really span the space of all possible directions. And what we did now is we took a sparse set of locations for which we acquired the full Donaldson matrix in this very slow process. We then, from that, learned the PCA space. And for all the intermediate locations, we just did a sparse sampling of a very few pairs of wavelengths. And then from that, we covered the full matrix again, okay? So that means for all the intermediate states, we just have these collections of 8 to 15 pairs. And this is sufficient to fully nail down the full information about the Donaldson matrix for this set of directions. And by that, we can sort of easily speed up the entire process. So here's a comparison of what you actually lose if you take too few PCA terms. So the top half of the sphere is already always the ground truth, and the bottom part, the reconstruction. You see it now here from two different positions of the turntable. Okay, so there are two different angles between the illumination source and the camera. And up to 20 components sometimes are necessary not to fully recover the angular dimensionality. But with that, we can now very faithfully measure materials and how they reflect light, so that we can afterwards re-illuminate these materials and represent them in arbitrary illumination conditions. So rendering it faithfully at 5600K illumination, or at 400 nanometer, which is blue, okay? And this fluorescent paint sort of, if you illuminate it in blue, just reflects red, or re-emits red, okay? And that's sort of the structures you see here. Here's some yellow. The yellow, green is fluorescence. It takes some part of the blue spectrum and re-emits it as green, okay? And you see it here, so you have this interesting mixture of a green ball with a bluish highlight, okay? So that's something you really just not normally see in other materials, actually. And here, just printing paper, which really takes a good part of the invisible UV spectrum and turns it into visible blue. And that's why paper is bright, okay? That's how it works, actually. And with that, we are sort of, for the first time, in the space of like really faithfully reproducing spectral effects on fluorescent materials, so that if you have a spectral environment map that is capturing all the illumination directions with spectral information, then we can faithfully render these kinds of materials. So this setup so far has just been for a single material, okay? And that already sort of like took quite some effort in order to get it faithfully reproduced. What we since then try to do is build a measurement device which allows us to acquire spatially varying materials, or fluorescent scenes, actually. So we have this light stage. Light stages have been developed by Paul Derbevec for capturing reflectance field. And our light stage is particular in that we can modify the spectrum we emit by each individual light source, okay? So this is how the wiring actually looks like. And with that, we can now sort of move a camera on this arc around the object. We can turn the object here on the turntable, and with that are able to acquire bispectral data. Okay, maybe do here. Oh, okay. Then I'm just going to show you what's happening. Okay, so here we have a set of Lego pieces, actually. So if you eliminate a set of Lego pieces, we were totally surprised by how much fluorescence you have in the standard plastics. Okay, so we have here a reference spectral sphere which reflects continuously at 99.something% over the entire visible spectrum. So that's exactly the illumination color, okay? And now we're gonna switch through the entire incident spectrum, and whenever you see here something which is not exactly that color, attenuated, then you see fluorescence, okay? And it's surprising what's all happening, like just with standard plastics. Up. Okay, so you easily see that there's now some green appearing, there's some red, blue, all at the same time, okay? So that's the effect you really have to model and to carefully capture in order to correctly reproduce appearance. So how do we do that? Well, we have a set of like 200 light sources of this kind. We have a bright white light source, and we have a set of 14 different spectral LEDs. So these are narrow spectrum wavelengths LEDs. And we have measured actually the spectrum of each of the LEDs. So we have roughly 3,000 different LEDs, like 200 different directions, bundled like this. And we are still continuously trying to update the types of LEDs we are using. In particular, we are looking for an LED which sort of spans this 560, 580 nanometer range, which seems to be problematic. There doesn't seem to be a material which nicely can be used for LEDs. So if anybody of you has some idea what to put there, we would be pretty happy. So you see this drastically different intensity spectrum of the individual LEDs, which sort of for the human perception, of course, has to be weighted by the V lambda curve. Okay, so that's how bright it is to the camera, not to the human eye. So the human eye here already is pretty weak, and it's really good. Okay, so now we have like 200 different directions, overall 3,000 different LEDs, and we have to acquire our data set. So that would mean for every possible position of our camera, we would have to acquire 3,000 images. Okay, so this easily adds up to weeks of acquisition if you don't do any additional thought on that. And what we try to explore is now the correlation between the illumination directions, between the viewing directions, and between the wavelengths. And we try to use compressive sensing in order to explore the inherent structure of these kinds of reflectance. Now, let's briefly look at what we have here at hand if we simplify the problem. So if we have fixed our camera to a single location, then we fix our outgoing direction omega O, okay? And now for every pixel, sort of, we try to figure out what is the response to any spectral environment map. The spectral environment map is represented like this. It's a 2D map having all the wavelengths here and all the possible incident directions here. Okay, so it's a 2D matrix. And similarly, the reflectance and re-emittance matrix can be represented as a 2D matrix of the same parameterization. Lambda in and all the different directions. Okay, so, and what you're going to observe for one outgoing direction, for one outgoing wavelength is exactly the inner product of these two matrices. It's not the matrix-matrix product, but the inner product of these two. Okay, so that's why we have, like, we can represent our illumination signal and the reflectance per pixel as a 2D matrix. And now we can try to, like, do compressive sensing on the structure of this kind of matrices. We can easily, in our setup, do multiplexed illumination. That is, we can turn on n different LEDs of different spectra from different directions at the same time. So for each setup, we're actually going to measure one particular observation per pixel. Okay, so, and we sort of get a camera measurement for a set of random illumination patterns times the reflectance we actually would like to recover. That's sort of our goal. And we're going to represent our reflectance field now in two different matrices. One being low rank, and the other end being sparse. Okay? So what's the intuition behind that? If you look at here is a particular matrix which we've acquired. You see here a patch of 40 times 40 pixels that corresponds to this tiny patch here in this card. Okay, and this is now replicated for all incident wavelengths and all outgoing directions or incoming directions. Okay, so that means, of course, it has a particular spectral response, and it changes slightly with the direction. That is, here's a group of directions in these rows where you see specular highlights. These specular highlights, of course, only appear in a narrow range, and therefore you can sort of like turn this into some sparse representation of the matrix. Okay, and the rest is relatively boring, actually. It's just these stripes, and they can be nicely approximated by a low rank part. So here's what we actually try to do. We would like to have our reflectance matrix C being assembled by a sparse and a low rank portion, and you can formulate that as this sparse plus low rank decomposition, which is successfully used in lots of noise-free PCA or noise-redundant PCA, for example. So you minimize the L1 norm for sparsity and the nuclear norm in order to reduce the rank. So that's what people have used already quite a bit. Our problem is slightly different. We have actually a compressive sensing problem here. We are not directly knowing the reflectance matrix yet, but we can just do measurements, probing of this kind of matrix. That is, we are just observing in our camera projections of these reflectance matrix, which we again going to decompose into low rank plus sparse component, sparse plus low rank, sorry, and we have a random matrix which sort of like then gives us sufficiently many projections. And then we have a iterative scheme for minimizing that. We use an augmented Lagrangian and sort of update the sparse part, the low rank part, and the Lagrangian all the time. And it's actually surprisingly simple to do that. What we have to do is, in order to minimize the L1 norm iteratively, is we do hard shrinkage. Hard shrinkage simply says, like, you take your matrix, from the matrix, from each entry, you subtract a constant threshold. If it's still positive, you keep it. If it's negative, you clamp it to 0. Okay, that's shrinkage. And you do that in each step of your iteration once for all matrix entries. And by that, you're reducing the magnitude of the entries of your sparse matrix further and further, and it converges to a good result. And low-rank approximations is done very similar. You would like to get a sparse representation in your singular values. So what you do is you compute from your matrix a singular value decomposition, take your singular values, and then shrink the singular values. Okay, so you take your SVD, you shrink your singular values, that is, subtract a constant threshold from your singular values, and then recompose the matrix. And by that, you have reduced somehow very little in each iteration the rank of your matrix. And this converges actually to a low-rank approximation. And putting all that together, we're actually going to get a scheme. Here, for example, a scheme or the result which we get for having here the incident direction now being split up into theta and phi. Okay, so this is the original full reflectance matrix of a mirror on top of a more or less diffuse reflector. Okay, and you see that in some part of our incident direction domain, we're actually going to see specular highlights here. And our separation nicely tears apart the specular reflection, which is very, very narrow and sparse, and the overall slowly varying diffuse reflectance. Okay, so that's really what the outcome of that is. And if we compare our sparse plus low-rank scheme, which really explores the structure of this correlation between different components, we are actually much better than other compressive schemes, which, for example, use a wavelet representation for this reflectance. So here's just a particular shot. Here it's a zoom in onto one part of this tree we've seen earlier already. So here is what you see as ground truth. It's pretty clear. And what we can reconstruct very slightly changes intensity and sharpness, and you see some noise in the very dark part, but it's much, much better than any other compressive scheme, which just uses wavelengths in order to represent that data. So really, it seems that with the sparse plus low-rank representation of our huge matrices, we're more closely modeling the actual data. So here's another reconstruction we get for a flower data set. Here, unfortunately, you see that the silhouettes are sort of slightly blurred. That happens if you have living materials, sort of. Even if we now reduce the acquisition time to like 2 hours, it was totally sufficient to like have the leaves move a little bit, and then of course you break all the correlation. But otherwise, you see that there's some nice fluorescence in the blue part in order to render the white flower leaves, much, much brighter. And here's like overall the reconstruction for a set of text markers, which of course second. Okay. So here you have a set of text markers. We can now sort of like change again the wavelengths, and you see how the different colors come up. Even though we have a narrowband illumination, you see all kinds of colors being re-emitted. And we facially, up to like some percentage at least, can recover this bispectral behavior, and at the same time correctly render nice and dense angular movement of highlights. Okay, so that's all nicely separated. This is the part which probably ends up being in the sparse part of the matrix, and the fluorescent part mostly going to be inside this low rank part of the matrix. The interesting thing is now we can actually extend this idea of exploring correlation. So far we have just explored the correlation between the illumination direction and the incident spectrum. And now we can actually go further and also correlate different views with each other. Okay, by that, our data just grows, so we are no longer looking at matrices, but actually at tensors. And these tensors can now be, again, separated to sparse plus low rank part. And all we have to do is now switch from a simple singular value decomposition to a higher order singular value decomposition. And all that it does is actually, if you have a third order tensor, you transform this tensor into a 2D matrix for each of your 3 dimensions, okay? So, and then you do singular value decomposition and shrinkage of your single values parameters for this flattening, for that flattening, for that flattening. You get a reduced rank matrices in these 3 dimensions. You average them, compose it back to a tensor, and you're done. And by that, you actually can now nicely explore the correlation between different views. And here you see just 3 exemplary views where you see very nicely that the overall structure between the views is very similar. And then there's here some shadows being cast in the different views by the camera, for example. And you see the specular highlights, which also move, of course, if you move your camera around. And this is the part that ends up actually nicely in the sparse part, while the rest seems to be more or less homogeneous and therefore ends up in the low rank part. Furthermore, here's an example of the kinds of shadows we can recover. Oops, sorry. Okay, so it's unfortunately not that sharp and not that crisp, the shadows, but otherwise it's still there, okay? And this shadow is something which drastically changes per view, therefore it's going to end up in the sparse part, not in the low rank part. Okay, what we faced actually is we sort of like got up to a 20 times performance increase in acquisition, which really gets us from a week down to a couple of hours, still doable for an entire object. But we have lots of problems still with very low signal responses, like very dark parts of the scene really just get completely noisy because it's going to be overlaid by bright reflections. And the reconstruction time is something we now worked on for half a year, actually, because doing a singular value decomposition is 2,000 times per pixel. So times 1 million pixels or 2 million or 4 million pixels really is something that, again, takes days if you are not careful doing that. Something we have observed is that in the compressive sensing literature, there's hardly anything being written about how you have to use your measurement matrices. There are some weak signals you need to establish for the measurement matrix in order to make the entire scheme work. But we observed that the standard matrices which were proposed sort of produces this kind of measurement in our camera. So that is for each random set of illumination we put on, we almost observe the same image in the camera. It doesn't change because like what's happening, you have 3,000 LEDs on a sphere, you randomly turn off 50%, so on average you have like half of your LEDs on, and that half is sort of like always illuminating your scene from all kinds of direction, and you don't see any major effect any longer. So therefore we are trying to optimize our illumination patterns in order to increase signal-to-noise ratio quite a bit. Yeah. So that's something we found interesting that we haven't found any link to in the compressive sensing literature that could be these kinds of dependency of what the illumination or the signal should be compared to the data you would like to measure. Okay, so future directions, of course we would like to do the full bispectral measurement also in our light stage, having a spectral filter in front of our camera, of course then extending further the the acquisition time, so that we have to like explore even further correlations between the individual dimensions. We would like to build up a multispectral material database in the near future. And the other part of what I'm actually trying to do is like measure materials in the wild. And here I'm actually fully agree with Bart's talk yesterday. We need to also look at like how can we use rich data for doing material acquisition. It's not, I mean, why should we just focus on molecular single image recovery of materials if we now have so much more richer data available? I mean, it's so easy to take a small video clip or a stereo video clip, which comes now easy if you have a stereo camera inside your handy, which is going to be around in the very near future. So therefore, I think having depths, having multiple views, having a dense light field in your acquisition, sort of like gonna definitely help in order to distinguish materials in the near future. Okay, with that I would like to thank you for your attention, for inviting me, and all my collaborators for helping me in this work. Thank you.
So time for questions.
Thanks for a really inspiring talk. If I understand correctly, fluorescence has a temporal delay in the emission. Can that be exploited for measurement or some tasks in computer vision like geometry recovery? Because I think you can now measure that with transient imaging techniques.
Yes, so, okay, there is some temporal component to that. I mean, if you look at the acquisition time we were fighting with at the moment, we are far beyond that range of resolving that. You're right, now we have like the first cameras being able to do transient imaging, that is time-resolved imaging at the picosecond range actually, so that you should be able to distinguish the surface reflectance probably from anything that happens beneath the surface. You're probably going to have to be rather careful to tear apart fluorescence, which is more or less an instantaneous effect, from phosphorescence, which is again introducing a wavelength shift, but has of course a way longer re-emission time. So it's going to be, if you have any part of phosphorescence in there, then your effect of illuminating at once going to trail off very long time. So I haven't seen any data on that yet, but it's going to be interesting, I guess, to explore that further. Yeah.
I had just, sorry, this is just a quick comment. You said you're having problems with this kind of 560 to 580 nanometer.
Yes.
How about just using a very, very bright white, so spectrally flat, and then a filter? Why can't you do that?
Well, we can probably do that. It's difficult to mechanically put that into all our 200 light sources then in that case. Probably we should do that this way, yes. Yeah. It's waste of energy, of course.
Yeah.
Otherwise.
Okay, I have two questions. The simple question is, I noticed that you used near-infrared LED.
Yep.
As one of the LED set.
Exactly.
So do you have any particular applications for that?
That was intended to sort of like analyze biological tissue. Of course, you don't see any fluorescence in there, but it's sort of, the hope was that we sort of get some deeper insight into the biological materials. We haven't fully explored that yet.
And the other question is, we empirically found that the fluorescent basically obeys very closely to a pure Lambertian model. So I think it makes sense to separate spectral component and fluorescent component before you're sampling images to reduce the sampling.
Yes
and
no.
Make sense?
Yeah, I mean, sure. I mean, for sure, there's like, I mean, fluorescence to main part is diffuse. What we really have seen in some of our data, it's not perfectly diffuse though. So you still have some angular dependency to it. And now it's just a question like, can you live with approximating that with the Lambertian or not? If you can, then for sure that's a great way of improving measurement speed, because then you don't have to care for measuring the fluorescence for all kinds of directions. Otherwise, you really have to perform. You do that.
Well,
Yeah.
actually, that's very related to the question I was going to ask, which is what is the angular distribution of the light which is emitted after fluorescence? I mean, can you do? It doesn't look like you can do very much shape from shading of fluorescent.
Oh, well, I think we see this afternoon a talk by Imari Sato, which exactly explores that very nicely. I mean, it's close to diffuse for most parts. I mean, I think it gets more complicated if you really have some complex lacquer, multiple layers on top of that, then things can get weird, as well as if you have very particular structure inside your material, then everything sort of like can be directed. It's not as clearly not as strong as any specular lobe. So okay, it's close to diffuse, but it's not perfectly diffuse.
So actually, I was noticing that in the approximations, the blue and the reds, there was quite a bit of difference there. Sorry, the
Yes.
greens and the reds. Not the blues.
So sometimes we still have some confusion in there, which we currently attribute to problems with our measurement matrix. So it's not powerful enough to resolve all that. So that's really something we're still playing around with, like figuring out how you have to come up with a perfect measurement matrix to nicely tell apart all these components. Yeah.
So if you have shape information of the object, then can you make the number of images you should capture can be
Yes, okay. So if you have shape information, then it's way easier to correlate the sensing between different views, because then now you can really fixate on the same surface point observed from different views, which we actually did for our multi-view setup. So we had the flat cardboard, actually, this paper, it's printed paper, actually. And then you can very nicely correlate the different views. If you cannot do that, then you're comparing samplings of different materials. And there, of course, you might not see any correlation. So it's so easy to lose correlation in your data as soon as you do any misregistration or not perfectly making use of this, the 3D geometry.
Thank you. And I have another question. In terms of rendering, if you want to apply this model, I mean the bispectral BRRDF, it sounds to me it requires a lot of computational cost to render. For example, if there's an interreflection part, then of course we have to consider about the geometrical energy interaction.
Well, I mean, it's not so much more work than having a spectral render overall. You know, I mean, of course you have way more data for representing your bispectral BRRDF, but it's otherwise you need a spectral renderer, so you have to be able to transport or sample your incident wavelength, and then you just look up what other wavelengths you have after the first transmission and use that simply. So it's not extending beyond what you have to do for spectral render anyway.
Okay, thank you.
Okay, thank you very much.